We believe that this school will be a strong seed for the formation of a working group on astrobiology here at Observatório Nacional. So I hope you can enjoy the school, okay? And I would like to thank the other members of the organizing committee, Dr. Isa Oliveira, Dr. Vinícius Bordalo, Dr. Renato Duque, and also Dr. Jailson Alcaniz. And I would like to especially thank the invited speakers. Thank you very much for coming, Dr. Jacqueline Sauer, Dr. Dave Kathleen, Dr. Ted Bergin, and also Dr. Mario De Pina. And thank you, all of you, for coming, okay, to making possible this school. So I would like also to thank the presence of our director, Dr. João dos Anjos, who will also say some words.
Well, we are a little bit late. Then I would just like to welcome everybody. Thank the speakers for coming, and also the students. That ON has a very aggressive program for graduate courses and also for young researchers, and I think that's a good opportunity to get on this theme. This theme is very interesting. That is a growing area of astronomy, and I hope this will start something here, a seed of astrobiology here in Observatório Nacional. Then thank you for coming. I hope you enjoyed Observatório Nacional and also our city. And yes, welcome.
All right. Hello. Since we're a little bit late, I'm going to be very brief and reintroduce to some of you the first speaker of the day, who is Dr. Ted Bergin. He's went from Villanova University to University of Massachusetts, where he gets his PhD, and then he did a tour at the Center for Astrophysics at Harvard, and joined the faculty in the Department of Astronomy at the University of Michigan about, I think it was 2003, yeah, where we overlapped for a while. He has been working several different aspects of planet and star formation, with more recent focus on water and the formation of molecules that later are used for life. I think he insists that if you actually dive into a comet, it would be pretty much the same as going to Copacabana, with less crowded, I guess. And so he will talk about making a habitable planet.
Thank you. So did I turn this thing on or did I turn it off?
That's okay. Well, it's a pleasure to be here again, and I'm looking forward to learning a lot of things myself along with you. So I'm going to really have a lot of astronomy in this talk, in this series of talks. So, when I say making a habitable planet, I'm going to be focusing on the big picture, which is, where did everything that goes into a planet come from? And then ultimately, how can you take that material and construct a planet that has the right stuff? And so that's sort of a generic statement. So what is the right stuff? And again, I'm going to be very broad, right? So you want to think about what we're made of, right? And so this is just a plot by mass of what our bodies are constructed of. We're mostly water. That's where the oxygen comes from. And of course, we have a key component of carbon, but the most abundant non-inert elements, that is reactive, oxygen, carbon, hydrogen, nitrogen. That's really, if you want to think about astronomy and many of the things that we observe, it's these species right here, or elements. Okay, so dominance bow, water, and then of course carbon is key for the chemistry of life. So the chemistry of life is the chemistry of carbon. And of course, another big focus, if you want to think again astronomically, is water is the medium of life, and so where did the water come from? And I'll talk a bit about that. And of course, how does the planet get it? All right, so what is our planet made of? Here is our wonderful world. This is my favorite picture of our planet. And it's mostly silicon, oxygen, magnesium, and so on and so forth. So it's different. Instead of carbon, hydrogen, oxygen, nitrogen, here we now have things that are, if you will, sand. And so where did that stuff come from? So there's sort of two sides to this, right? Where's the stuff that life is made of, and where is the stuff that the planet is made of? And you can separate these two, but of course they go together in some way. So the ingredients, such as they are, we need a rocky planet, apparently dominated by silicates, but what we don't exactly know is that the only outcome, right? We need the materials of life, and so that's what I call the volatile elements. These are actually the elements, the stuff that life is made of are actually the elements that are the hardest to incorporate into the rocks out of which planets are made. And that's an interesting statement, right? That may tell you that there may be a diversity of outcomes that are possible. So the volatile elements here are carbon, oxygen, nitrogen, okay? But of course, for life, we need other things, phosphorus, and so on and so forth. And I'm going to make up a new term that I hope to promulgate into the world, can we make a world chemically habitable? So we have this concept of a habitable zone that is the right distance away from a star where water can exist as liquid on the surface. And that's an interesting astronomical construct because it allows us to observe a planet, ask, is it a terrestrial-like planet? And it is at the right distance from the star where we think it could potentially have water. And so the question is the water there? Is the carbon there? Is the nitrogen there? Is all the stuff that life needs present? And so that's sort of the frame of which I'm going to construct many of these lectures. And I don't know the answer, which is great for students, right? Because there's so much more work to be done that can be done over the next 10 to 20 years where we can try to understand some of these questions. And it's all from an astronomical perspective. So the first lecture is I'm gonna look at our planet and understand something about life. When did it originate, and put that in the timing with an understanding of the construction of a planet like the Earth. So the context of planet formation. The second and third lectures, I'll talk much more about the way astronomically you can go about studying origins. And so that's going to trace the formation from the beginnings of the interstellar space, how you make molecules, how you make the so-called molecular cloud, which then collapses to make stars, and then that collapse, you have a star and a planetary system, and so on. And I'll also talk about chemically the perspective in the solar system. We have other things that we can use to trace our origins, and that is meteorites, the rocks that are perhaps remnants of things that formed billions of years ago, comets, and try and tie all these things together and trying to understand how we can make a planet that has the stuff that we need on it. Okay. So one question one might ask is, we focus a lot of our understanding of life on the basis of us. We have one data point, and you're looking at it, right? So that's all we have to understand life. And so you might want to understand, well, is it possible that life could come from other elements beyond carbon? And so one of the reasons why carbon is the basis of life is it actually has the most available chemistry, if you will. It has 4 bonding sites, so it can bond with oxygen, nitrogen, hydrogen, multiple ones of these. It can bond with itself, and it makes network lattices. And also, when it bonds with itself, it can have a very strong bond. All these things are good, all right? And even when it's bonding itself, it can still bond with other things. And so perhaps in a way, the available opportunities for the chemistry leads naturally to carbon to be the basis. Now, there is another potential element, and that is silicon, that has the same number of bonds of carbon. So you might imagine where that may come from. So here, this is Spock. You may know of him, I don't know, bonding with a silicon-based life form native to Janus 6. I got this from my other geek friends. And then I found that Silicon Dreams, that's the silicon woman there. and the buff geek. So we have silicon here, can bond to itself, same as carbon. All right? It has 4 bonds, but it doesn't form the double bond, so that's one slight negative for silicon. And actually, it's very unusual to have large chains of silicons. But one of the things I think that makes it unlikely for this to be the basis is that if you look in the initial conditions, all of the rocks, if you will, that are out there in space, all the silicon is in the rocks. It's not really out there in the gas. It's not really reacting and finding many other pathways to do different things. It's all stuck in the solid state. So it's highly, I think, unlikely for you to have silicon-based life. But again, we have one data point, and so that's an important perspective to just remember that we're working off of incomplete information. Okay, so here's where the astronomer goes off into biology, and Mario can yell at me if I go anywhere, but cells are the fundamental units of life, if you will, of working units. All right, now historically, if you look back in time, and even today, we see 2 different flavors of cells. There's stuff called prokaryotes. They have no cell nucleus, and they existed before the ones that do, which is the eukaryotes. All right, and they're always single-celled creatures. An example of this is bacteria. And these things outweigh and outnumber eukaryotes. So if you want to think about life on a planet elsewhere, life on our planet is dominated by these things, not visibly perhaps, but it's in terms of number, they're what life is, and this may be more likely for life elsewhere. And then there's eukaryotic. They contain the cell nucleus, and that protects the DNA, and it's the basis of multicellular creatures. So here are 2 example cells, right? So this is the prokaryotic, and here's the cell nucleus, and so the cell itself, has a nice little fortress, right? It has a membrane where you wall off the genetic material and protect it against attacks from other chemicals and such. All right, so this is, you can classify life basis on the DNA. And again, I'm just doing very broad brush stuff here, and you'll see where I'm going in a minute. So you can go by cellular division, so there's prokaryotes, eukaryotes, and then if you look at the DNA relationships, the prokaryotes divide further. So there's bacteria and archaea, and the eukarya branch off of that. So this is what's called the tree of life. And there's another representation of this, which I have. So these are the 3 domains of life: bacteria, archaea, and eukarya. And I'm not really going to dig too much into this. I'll leave that to our biologist here. But this is an example of the tree of life. And I have this up in much larger form on the wall of my office because I think this is just amazingly fascinating. So what is this? These are the genetic relationships between thousands of organisms. And the oldest ones are over here. And they shoot basically straight back down to the sort of, you would call, the root of the tree of life. So there are organisms that actually probably are representatives of the first cells, if you will. And all other creatures branch off from there. So they sort of branch out this way. And just to show you that, yes, we are on here, we'll zoom in here. And there we go. It's us. And then our cousins here, if you will. Genetic cousins. All right, now, if you want to think about life and from a chemical perspective, in a way, it makes it easier to approach astronomically. All right, if you want to understand the basis of the chemistry of life, then we could ask, can we search for molecules that are related to this, the chemicals that life uses, or perhaps maybe are precursors to that. So it's important to understand some aspects of the biochemistry of life. All right, so there's proteins. These are the working units of the cell, and they are a sequence of amino acids, and life uses about 20 amino acids. And proteins are what we call enzymes. They're catalysts, and that is they participate in cellular reactions and facilitate chemical reactions, but still remain behind to continue facilitating. All right, another example here is adenosine triphosphate, and this is the battery of the cell. And all life uses this molecule, ATP, to store energy. So when I'm wandering around here, I'm using up stored cellular energy that's actually stored in this one really cool, neat molecule. And then, of course, the big ones, the nucleic acids. There's deoxyribonucleic acid DNA that has the genetic code, and the simpler form, RNA, which helps to carry out the genetic functions. And these things, there's a chemical perspective here at the back where you have, OHs sticking out. That's common for alcohols and sugars. There's the CO double bond in different spaces, carbonyl groups, amino groups, that's in amino acids, and other things as well. And we see this in, some molecules in space in simpler form. And then this is the basis of life. So the composition of DNA, and again, this carries basically who you are and passes on that information to subsequent generations. And so you have this backbone here, right? And this is a sugar and a phosphate. So, the phosphorus is understanding where and how phosphorus got to planets is another interesting question. Harder to get at, actually, than the carbon, hydrogen, and nitrogen. And then the genetic information is encoded here in this, if you will. This is the ladder here, and these are the rungs of the ladder. And there are 4 bases here. There's adenine, guanine, thymine, and so these are just beastly molecules, very large, very complex. And the pairing of this, the A will only pair with the T, and G with C, and so on and so forth. And that's forced essentially by the chemistry. So there's, if you want to think about biology and chemistry, it's clear that you have things probably started out, and I'll talk about this a little bit, as some sort of organic soup in terms of chemistry, and then it made its way to reproductive chemistry and chemistry that can reproduce itself, and we call that biology. Okay, so all life on Earth uses DNA to store the genetic information. All life uses water as the medium. All life uses that one molecule, adenosine triphosphate, to store energy in the cells. And all that points back to a single common origin, something that worked and it took off. All right, and the how that happened is not the realm of astronomy. It might be perhaps considered the realm of astrobiology, but what we want to understand astronomically, from my perspective, is how you made things available such that this could happen. All right, and so this is DNA, and from an astronomical perspective, again, me, I observe OH, I observe N2H+, which is not this. We see NH2 sometimes, but this is a beast. And how you get to here, and making something like this, and can that be common? It's really a fascinating question. It's a very complex molecule. So we want to get from chemistry to biology. How can we do that? We need energy. We need a liquid, and we'll talk about water and whether water is common in planetary systems and available in planetary systems as they form. And you need simple organics, amino acids. You need carbon at a basic level, right? And so you start off with very simple things that either are supplied to the planet, we call these monomers, or perhaps the planet made the monomers and you just supplied it the carbon in very simple form. And then you combine them via chemistry on the Earth into more complex things. So eventually, the protein. So you take the amino acids and you make protein. So that would be the polymers. And then so on, you have this march towards complexity. And to do all these things, you need energy, water, and at least the organics, and then you have to concentrate them, stick them in some place so that they actually find the reaction pathways that work. Probably lots of different pathways were tried on the way to life. And then you need energy somehow, so you could get energy from the chemistry itself. Or perhaps you may harness energy from the Earth. And of course, you need the liquid medium. So one example of how you might begin your march towards complexity was done by Stanley Miller in his thesis, where he took water vapor and he put a mixture of gases that stimulate the early atmosphere, what he thought at the time was the early atmosphere of the Earth, and stuck that and mixed it with water. And then he gathered it into a chamber where he then exposed it to lightning, energy. Okay? and gave it some energy then, and then condensed it in the bottom and let it sit there for a while and asked what happened. And so he put very simple things, you know, methane and ammonia and stuff, and he stuck that and with water, exposed it to energy, and out of this came a liquid that actually had amino acids and organic compounds. So it was one example. It may not be the only example, I'll talk about others, about how the planet itself could begin to take simple things supplied to the planet and make the beginnings of this march towards complexity. So another example of things that actually have larger molecules and may have provided sort of a jump start to the chemistry of life is that meteorites, things, rocks that fall from space, and this is one example. This is a piece of the Murchison meteorite, a meteorite that fell in Murchison, Australia. And this particular rock is basically rich in organic species. Over 100 amino acids are found in the rock itself, falling from the sky. And life, again, I said, uses 20. So it obviously is providing things that life doesn't use. So that suggests that if rocks falling from the sky had complex organics in them, well, where did those things come from? What is the process that leads to those organics? And are those important for the origin of life on the Earth? In other words, if rocks falling from the sky, did that jumpstart the chemistry? We don't know the answer to that. We know that rocks falling from the sky have these things in it, right? And whether that was important or not, we don't know. But it's part of the picture, if you will. And another example of part of the picture, and this is something that's come out over the past, I guess it's 15 to 20 years, is that there are vents deep in the ocean where the temperature can exceed here in Fahrenheit, 750 degree Fahrenheit. So that's above boiling, but life actually is found and thrives in these environments. And you have a geothermal, so the Earth is providing the heat and the energy here that chemistry potentially could use. So if you provide the simple things to these types of environments, and they certainly existed on the early Earth, maybe life could have started in an environment such as this. And in fact, if you look at the genetic relationships, the species that are found in these environments are closer to the root of that tree of life. So it's suggested, but it may be that this is just where life found a nice place to survive, right? Because it's deep in the ocean, it's safer. So maybe life originated elsewhere, and this was just a nice environment where things could go. We don't know. Okay, so abiotic chemistry to biology, we need water, energy, organics. We take chemical energy. Eventually, we start harnessing the energy from the sun. You need water and organics. You build superorganics, make polymers. Somehow you get spontaneous generation of cell, and then you lead to reproduction. And how you get here, I don't have a clue. And that's not actually what I'm going to focus on. I'm going to ask, how we get this stuff into a planet, and then the planet can hopefully do something interesting with it. Now, from a perspective of astronomy and planet formation, it's the astro in astrobiology. It's useful to have a construct on how quickly this happened on the Earth, how quickly life originated, and how does that go into the time that it takes to say build a planet. Okay, so the first thing we have to do is we have to figure out the history of life on our planet, and we try to use fossils to do that. Of course, these are organisms that existed a long time ago and left an imprint. Now, it's actually not it's the minerals in the organism, not the water and the carbon generally that is leaving. It's the silicons and the iron and so on that leave the shapes behind, all right? And only a small fraction of living organisms are lucky to die in an area where they'll leave themselves behind, whatever that means, okay? Now, the fossils, generally, the really old fossils have no information on age. And the way that we approach age is using radiometric dating of the rocks in which the fossils are found in. Okay, so I wanted to go a little bit through radiometric dating because I think it's an interesting field and interesting to understand how we know roughly, give or take, millions of years, hundreds of millions of years, when life potentially originated on our planet, and how do we know, actually with some certainty, when planets were born. And so this is just one example. There are different atoms, and there are stable isotopes and unstable isotopes. And some of the isotopes, the unstable ones, decay to different atoms of either the different isotopes of the same atom or different elements entirely. And this process occurs over a defined time scale, which we call the half-life. So for example, uranium-238 goes to lead-206, and the half-life, that is the time to take half of a sample of uranium-238 and turn it entirely, that half, into lead-206, is 4.47 billion years. You have potassium-40 to argon-40, 1.25, carbon-14 to nitrogen-14, 6,000 years or so. Okay? And this is just another way of showing that. Now, this is the way, the common one, actually, I'm sorry, the way that we get the age of the Earth, for example, is using what's called lead-lead dating. So here you have uranium going to an isotope of lead, another isotope of uranium, so 238 goes to 206 lead, 235 goes to 207 lead, different half-lives, and then thorium decays to 208 lead, and that's the half-life. Now, interesting thing about this sequence is that, here's 238 going to 206. It doesn't go a direct route there. It goes all over the place. And you can see sometimes, this is 3.82 days it stays there, three minutes. And so the longest part of the chain actually is what sets the half-life, okay? And so in general, on 4 billion years, 4.747 billion years, you're going to take half of this and turn into this. But on the way, you're going to go through Park and a bunch of other things for very short periods of time. Now, the way you do this is you take a sample of rock, all right, and you put everything referenced to a stable isotope, which in this case is primordial, so 204 lead is stable. So you measure the amount of 206 lead, 204, 238 uranium in there, and again, reference to that. So here we have, this is the radiogenic thing that's decaying down here, okay? Now, this is whatever was in the rock perhaps at the start, okay, of the 206, all right, that's whatever was in there in the beginning, plus whatever then will decay from 238 gives you the product, right? Now, if I measure, in this case, 238 and 204, this thing right here, okay, and then I also measure the product, 206 to 204, put this on the x-axis here, put that on the y-axis, then I have just a simple line here, y equals b plus mx, so there's the slope, right? So the intercept is the initial amount that was in the rock, and the slope is something to do with the half-life and the time that is the age of that rock. Okay, and the way geochemists approach this is they do all of the different isotopes of lead coming from here, 238 uranium, 235, and 232 thorium, and ask, do I get the same age in each measurement? And that's what's called concordant dates, and that then tells you the actual age of the rock. All right, now, you can only do this if you have a closed system. That is, you're not adding any more of the product lead isotopes, or even the stuff that's coming out. So it has to be closed. That is, which a rock generally is, right? Now, when isn't it closed? When it's a liquid, right? So it's telling you something, the age of the rock, basically when it solidifies. All right. So you also don't always know the isotopic ratio that the rock, the initial amount. That's a problem, all right? And the way you can go around that is you can choose minerals that exclude elements. So for example, zircons, these are a very stable mineral. They actually exclude lead at formation, but not uranium. So any uranium decay can basically be directly traced. Another example is you can take daughter products that aren't included in minerals in general. So for example, Argon is a decay product, all right? And argon is a noble gas. It doesn't react with anything. So it's not in the rocks for the most part to start with. And you could generate it entirely from radioactive decay. So for uranium-containing minerals that exclude lead during, for example, during formation, for example, zircon, this is sort of the plot that tells you the isotope ratios that you expect and the age that it would be. Now, from the perspective of the Earth and the beginnings of the Earth, if we're using this as to set a framework to understand when life had originated, we want to understand when t equals 0 is. The Earth is evolving. And what do I mean by the Earth is evolving? The Earth is an active planet that is constantly resurfacing itself. There's wind erosion, there's rain erosion, there are oceans that cover 2/3 of the surface of the planet. The oceans move around over time, and so we don't have rocks actually that trace back to the beginning of the Earth. All right, the oldest rocks that we have on the Earth are on the order of about, you can go to places in Australia and places in Greenland where you can walk on rocks that are about 4 billion years old. Kind of cool. And we also can't always find systems that exclude lead upon formation. So what was done actually to get the age of the Earth itself was to use meteorites. And what was done by a fellow by the name of Claire Patterson is that it had very low amounts of lead daughter products. All right, and it was also low in uranium relative to lead. And this meteorite actually provided the primordial isotope ratios that then allowed us to unlock the timing for a whole bunch of different systems, and was able to age the meteorite at 4.45 billion years. And that gave you assume that the Earth, the age of the rocks in the solar system, if you will, are the same age as that. So the Earth originated sometime around 4.45 or 4.6 billion years ago. Now, interesting little thing, to do this, Claire Patterson actually had to figure out how to measure very small amounts of lead in rocks. And then he went and actually started looking at lead elsewhere on the planet and found out that at the time we were sticking lead in our gasoline and pumping that into the atmosphere. And it was found that actually the lead was polluting all over our planet, and then actually was bad for life. When you ingested it, it can actually lead to some developmental problems. And so he became a crusader. Because of this work determining the age of the Earth, he then became a crusader against lead pollution in the US, and led over time to laws that banned lead in gasoline and lead in paints and so on and so forth. It's kind of neat. So the modern methods start with what we now know are the earliest known solids in the solar system that are what are so-called calcium aluminum-rich inclusions in meteorites. I'll talk about that later. These are clearly the first solids to form, and over 70 meteorites have ages on the order of about 4.53 and 4.57 billion years. And so amylin, this is one reference that I use to provide that basic framework. All right, so when did life begin? When the Earth was born, it was a process where the Earth was the biggest thing around in its neighborhood, and it was attracting gravitationally lots of other rocks that were bombarding it constantly. So it was a very violent process. Lots of things falling from the sky, impacting the Earth. And some of them were actually big enough, if oceans existed, to actually what we call sterilize the Earth. If you think you need a liquid medium, water, to foster and facilitate chemistry of life, if you vaporize that entire liquid medium, then you perhaps could stop any march towards complexity in its entirety. All right? Now, the craters that existed at this period, in the beginning as the Earth was being born, are lost. Earth is repaving itself, right? So we don't have a history of the impacts on our planet, but we do have the history from elsewhere, and you can use the moon to tell us some aspects of our lost history. So here's, this is North America. There's some of the craters that are known, and here's one area of the surface of the moon, and you can see that, this does not equal that, right? There are just craters everywhere, and so what we use actually, and I have a plot of this later on that I reconstruct it. Different parts of the moon have different amounts of craters on them. And amazingly, pretty coolly, we actually had people on the moon at one point in time. And they brought back rocks. And those rocks could be radiometrically dated. And so that you could use that radiometric dated rock, the amount of craters that are there, and you find that the areas of the moon that are younger have less craters per surface area than those that are older. And you can use that to actually try to reconstruct something about the history of the Earth. Right? Now, what about oceans? Where were oceans present on the surface of our planet and when? We have some information of that, and that comes from these zircons, or zirconium silicate here. These minerals, they're stable to 1700 degrees Kelvin. They are not soluble, for the most part, in magmas, which is kind of amazing. And you can get the age of these things from lead-lead dating, and they have oxygen inside of them, where the geochemistry, and I'm just quoting what they say, is suggests formation from melting of a continental type crust interacting with a low temperature liquid hydrosphere. All that means is that the geochemistry is telling you that liquid water was present. All right? And this is an example from a fellow named Steve Moises. Here are zircons, different ages. So this suggests that the Earth had water on the surface as early as 4.4 billion years ago. Now, it didn't mean that water coated the surface. It could have been just in local pockets, and when the continents formed, and so on and so forth, is not something that I have any particular data on. So we have oceans about on the order of the liquid on the surface as early as 0.2 billion years after formation. Now, if you have an asteroid on the order of about 400 kilometers that can impact the Earth and raise its temperature to 2,000 degrees Celsius, and that's bad for life, it'll vaporize the oceans. You can have impactor on the order of about 200 that could vaporize a pretty deep ocean. All right. The last sterilizing impacts would have been on the order of about 4 billion years ago. And lest we worry about this, there are about 100 of these asteroids that still exist. But their orbits are stable and not crossing. So unless we go in and screw with the asteroid belt, we're pretty safe from this happening. So now, when did life begin? We have a context. We know roughly when the rocks in the solar system formed. We now know that a little bit after that we had oceans on the Earth, or water on the surface. And we have an idea from the moon that the last sterilizing impact would have been about 4 billion years ago. Now, there are 3 lines of evidence that are used to sort of buttress the case for understanding when life originates. And that is the 13 carbon to 12 carbon ratio. Now, there's a radiogenic form of carbon that's 14 carbon. This is the stable isotope, 13 carbon, and the 12 carbon. There's something called stromatolites and microfossils. Each of these give, sort of some evidence as to when life originated. So what is this? So the 13 carbon to 12 carbon isotopic ratio is the first one, okay? Now their normal abundance is roughly about 1 to 90. That is, for every 1 13 carbon, there are 12, or 90 12 carbon atoms. Okay, so the 12 carbon is the main isotope. All right, so the living tissue metabolizes carbon 12 more easily than carbon 13. So it has less 13 carbon. Now, the environment has this ratio, and the chemistry in our bodies basically elevates it by using more carbon 12, and then 13 carbon is sort of then left behind as a waste product. Right? So we actually see this in fossils, that fossils have more carbon 12 relative to carbon 13. So this is the inorganic carbon field in their sample. And so some rocks in this actually have this deficit of 13 carbon. So this is a deficit. So this is the normal ratio over here, 0. This is from Holland. Anything below this, so here we have some rocks that have carbon in them. They're 3.9 million years, or 3.9 billion years old, and they have this deficit of 13 carbon. Now, there's no fossils here. There's just carbon in the rock, and it has an odd isotope ratio. Right? So some rocks show evidence for this low 13 carbon abundance. And you could suggest, well, maybe this is evidence, indirect evidence, that life was present there. It metabolizes this 12 carbon more readily and left this signature behind just in the elements, all right, the elemental carbon. Some issues are that some of these rocks are what we call metamorphic. That is, they are altered under high pressures. That means they've been exposed to high pressures. And it's the types of rocks where you generally find fossils are what we call sedimentary, where the rocks have been laid over successive generations and much more gentle than subject to high pressures or something like that. Now, if the rocks are volcanic in origin, right, that's lava that's melted, and any signature will be lost. So there are some arguments in the field as to whether this actually is telling you that life was there 4 billion years ago. Okay, another example is something called stromatolites. So these are colonies of bacteria that create a sort of layered structure. So they begin down here, and then another colony grows on top of it. The colony on the bottom actually dies, and the one on top sort of lives off it, and they build their way up like this. It's kind of mimicking, sedimentary laying of rock structures. Now, stromatolites actually do exist in one place on the Earth, in a so-called Shark Bay, West Australia. I talked to one of the biologists who goes there, and she was swimming around. I was like, well, do you have to worry about sharks, right? Actually, it's named Shark Bay, but apparently sharks aren't there. I don't know what that says about the name, but in any event, you can actually see these things, and they actually have evidence, at least for ancient Earth. So Archean is billions of years ago. It's an age when life was beginning to originate on the Earth. So here are rocks that show layered structures, very similar to modern stromatolites. Right? So these rocks on the order of about 3.5 billion years show almost identical layered structure, and are suggestive and consistent with a very shallow water environment that is similar to where we see the stromatolites today. And when I talk to the origins of life researchers about this, I imagine different people would give you different answers, but the claim is that this is perhaps the most solid of the 3 lines of evidence. But again, I imagine if I talk to different people in this field, they would give me different answers. And of course, this could be mimicked perhaps by some sort of local sedimentation process. Now, another line of evidence is what are called microfossils. So these are very tiny fossils, and this is an example of one that appear to be segmented, somewhat similar to some bacteria on Earth. And this proponent of this is a fellow by the name of William Schaff. There's others. And these are found in rocks that are 3.5 billion years old in Australia. And so here's modern organisms, and this is what one of the fossils look like. Now, if you go and look in the literature about this, that there's a lot of controversy as to whether these are exactly due to life. And in fact, if people have looked at the actual chemistry of these things and found that these particular organisms are filled with the mineral magnetite, which actually is not anything to do with life, and it's suggested that they argue that the ones that Schaff has seen actually are not microfossils, but actually due to something just due to geochemistry. But then the same authors have their own papers where they present fossils that, to my eye, untrained eye, look identical to that, and claim that those are evidence for microfossils. So it's an interesting thing from an outsider to look at this. Don't know what that means, but what it tells you is that we have 3 lines of evidence that point to the fact that life originated or was present. Life like this. This is not just simple chemistry. This is biological reproduction. Was present on the Earth as early as 3.5 billion years ago, maybe 3.8 billion years ago. Very shortly after the Earth stopped getting hit by big rocks from space. That's very suggestive, is it not? But again, this is indirect. Now, all right, so that's kind of interesting. how do we get there, is again a fun little mental construct. So we want to then very quickly make DNA, or something that operates the same way as DNA. Now, DNA itself we think is too complex to be the thing that carried the genetic code in the initial organisms. Right now, DNA needs both RNA and proteins acting as enzymes to reproduce itself. And RNA is actually simpler. It has one strand, not two. It does have a backbone. It does have a sort of a lower form of the genetic code. But in modern organisms, it still actually needs enzymes to replicate. So RNA can't replicate without enzymes, and enzymes need RNA for creation. So you have this sort of problem here that, RNA is simpler and may have been the first thing that carried the genetic code, but it also has this reproduction problem. Now, in the 1980s, Thomas Cech discovered that RNA actually, in some instances, can operate as its own catalyst, that then it breaks that chain. So RNA needs to make the proteins that then operate to form itself, but RNA could actually carry the functions of the proteins as well. So life may have started in what's called an RNA world. We're living in a DNA world today, where you have proteins that catalyze. It operates as the protein, as a catalyst, and it stores the genetic information. So, chemistry to biology in 6 easy steps. This is well, lots of BS here, but this one. We don't know, which is really awesome. It means there's lots of great science to be done. So you somehow started with a soup of organics. And what generated that soup is a question. Maybe some sort of atmospheric chemistry a la Miller-Urey, maybe deep sea vents. It's absolutely clear that things were brought to space. Maybe that brought from space. Maybe that helped. We don't know. All right, then we somehow concentrate. So, the best way to perhaps do that is to have some sort of, lake or something. You stick the organics in there, and then it evaporates, and you make a pond, or even less than that, right? And the organics stay in there, and so you concentrate them together, allow them to meet each other more frequently, react, and find a bunch of different pathways. You get the short strands of RNA, spontaneous membranes, pre-cells, and then we have our first true living organisms, and then you operate under natural selection. Okay, so this is the percentage of oxygen at today's level. So oxygen is a product of life, oxygen in our atmosphere, and we have an atmospheric expert here that can tell us all about this. And this is one idea of how oxygen may have come about from about 4 billion years to get today. And one could draw different lines depending upon different sets of data. All right, so evidence points to life on the order of about 3.5 to 3.8 billion years ago, right after the sterilizing impacts. And so that tells you that the transition from chemistry to biology does not take billions of years. And then you have the first eukaryotic organisms, if you will, the step towards complex life. So actually that took longer, right? So you got, the planet is born somewhere over here, you get the first life, and then getting real complex, and then multicellular organisms, that took billions of years. Okay? So, now I'm going to seg and try and connect this to something where I actually have a little bit more knowledge, and talk about the astro in astrobiology. So we're going to talk about planet formation and star formation very briefly. So everything starts out in what we call a molecular cloud. So space, diffuse space, has the elements strewn about, dominated by hydrogen, the most abundant element in the universe. Okay? So the interstellar medium of the galaxy. Some event in the interstellar medium, what we think is actually there are flows. The supernova explode. They provide energy to the ISM that pushes things around. It's a very dynamic medium. Some flows of the hydrogen gas swim together, hit each other. There's a shock, elevates the temperature, and you then cool down, they get a little bit denser. And when you get denser, you're able to block out the destructive effects of starlight, which is why everything's mainly in the elemental form, because molecules can be very readily dissociated from basically just the interstellar radiation field. So things get denser, molecules form, and you make what we call molecular clouds. These are about, so the average density of the ISM is about one particle per cubic centimeter. Molecular clouds have an average density on the order of about 1,000, so you're diverging a bit, and the temperature of the molecular cloud is typically about 10 degrees Kelvin, whereas the temperature of the generic ISM is about 1,000 Kelvin, give or take. Regions of the molecular cloud collapse to form a protostellar core, a dense core, something that's even more centrally concentrated by a couple of orders of magnitude. Still stays cold until a star is born in the center, and then you have thermal gradients. And then you have a rotating collapse. It leads to, this thing is rotating, it collapses to a disk, the star, okay? There is an outflow, so there's material expelled as part of this process, and eventually you get rid of all the surrounding gas and the disk, and you're left with the main sequence star and planets. So the molecular cloud lifetime is on the order of about a few million years, maybe 10 million years. And then the protostellar phase is somewhere on maybe 10 to the 5th to 5 10 to the 5th years. The young star, this phase also is about 5 10 to the 5th years. The lifetime of the disk, I'll show you a little bit about that. It's on the order of a few million years. So the whole process takes on the order of tens of millions of years. All right, so this is the little bit I'll do on planet formation, and we have an expert in the audience as well, Jack Lissauer, that's going to talk a lot more. But I just want to do this just to provide context for how I'm going to try and stuff the elements that light needs into the stuff that planet uses. All right, so the paradigm of planet formation is that you have a coalescence of solid particles. So the ISM has two components. I'll show this in the next lecture. So you have the gas, talked a lot about that, right? Hydrogen, carbon, oxygen, so on and so forth. There also is a solid state component. That solid state component is mostly silicates, but also partially carbonaceous. All right. The typical size of this solid state component is on the order of about 1/10 of a micron. All right. So tiny little grains in space. They coalesce together, have a gigantic party actually, to make basically things that are 1/10 of a micron size to some big things such as what we're standing on right now. And the actual physics of how this is done is really awesome and fascinating. And so you get your rocky planets, and then the big rocky planets here, the ones that are a few to 10 Earth masses. Again, I don't know the exact transition, but Jack does. Accrete gas and then form gas giant planets. Now there is another way actually to sidestep. This is if you will, you make a core first, which then can either make an Earth. If you make a really big Earth, you can make giant planets. There's another way actually to make the gas giants, and that is to directly collapse from the gas in the planet-forming disk itself via gravitational instability. And this is the preferred scenario, although there are planets that are found at far distances from the star that perhaps may have formed by this process. Okay, so the core accretion model, you have the coagulation of dust. You take these submicrons dust and you get to a few hundreds of meters, and there are interesting pitfalls from this tiny scale to this scale that have to be overcome. And there has been some actually recent really interesting discoveries and work that perhaps suggest how we might get there. Then you have the runaway growth of the largest bodies to about 100 kilometers of size. All right, these are planetesimals. Then when you get to 100 kilometers, you hit what we call the oligarchic growth stage. That is, the biggest thing wins. All right, and then there you get the true formation of the protoplanet. It gobbles up everything in its vicinity, and you get your rocky core. All right, and that rocky core, if it grows to big enough, can make the gas giant, and it may stay as an Earth. Now, chemically, what are these things made of? There's one approach to understand this that comes from the planetary science community. And it's typified by a textbook by John Lewis that is still used today about the physics and chemistry of the solar system. So here is temperature, and this is pressure. And these are different elements that condense at different temperatures and pressures. And the idea that Lewis wanted to convey by this is that if you formed at different temperatures and pressures, you would incorporate different elements in a relative sense. All right? So, it's easier to incorporate magnesium and silicon and oxygen, and it's somewhat harder to incorporate some of these other things down at lower temperatures. Okay, well, that's interesting. I think a more salient point, rather than talking about the minerals, actually comes from the harder part, is actually getting the carbon and the oxygen. So water, for example, condenses at 100 degrees Kelvin. All right, and that's kind of amazing, right? So whereas the silicates condense at 1500 degrees Kelvin. So it's a lot harder for the ices and the rocks, or for the rocks, to incorporate the quote-unquote volatiles. And that's actually almost all of the carbon, a significant fraction of the carbon, the water, and all of the nitrogen. So let me do this in a little bit easier to read format. So there's what we call the refractory component. These are silicates, carbonaceous grains. There are big carbonaceous grains. And we see these are present in today's interstellar dust. These things are the seeds of terrestrial worlds, although, as I will show you, the carbonaceous grains are not part of the formation of the Earth somehow. The Earth is made mostly of the silicates. All right, so these things we see in space are the seeds of terrestrial worlds. Then we have the volatiles, so H2, helium, water, organics, CO, methane, molecular nitrogen, ammonia, noble gases. All right, these things you need to have the refractory components stay as solids until about 1500, maybe 2000 degrees Kelvin. The volatiles make a transition from the solid state to the gas, and the planets are made of gas, right, at 100 Kelvin or so. H2 and helium, actually, that happens even lower temperatures than that. So they stay in the gas almost entirely unless they're accreted by a giant planet. So the water and organics are this intermediate state, okay? And then you have the things that are hardest to get, CO, methane. This is actually where most of the carbon is in CO. CO condenses at 20 degrees Kelvin. So if you think again, the planets are made of the rocks, or if you will, the rocks and the ices, not of the gases. If something's in the gas, it's not going to make its way into the planet. Okay. So how can we then get the stuff that life uses into a planet? All right, well, the planet itself is made of the silicates, so that perhaps is a starting state, although I'll talk a little bit about that in other lectures. Now, the surface area is dominated by the smallest grains, and so the volatiles in the gas need to then find a grain, hit it, stick, and stay as ice. And we actually see this in the interstellar medium. This process does happen, all right? Because again, in the coldest parts of the interstellar medium where stars are born, you're 10 degrees Kelvin. So even CO, which condenses at very, very cold temperatures, actually forms an ice in those regions. So this has to happen. In fact, we see it happens, and we see that most of the water in just the beginnings of planet formation is actually in the form of ice. All right, but what happens if you have these dust grains at 1 AU? You can actually do a very simple calculation to calculate the temperature. So you have the energy absorbed of one of these grains. Depends upon the flux of the sun at 1 AU, the absorption efficiency of that grain, and its surface area. All right, and you balance that by the energy that's emitted. That's the emission efficiency, the surface area radiating out to space, and then, of course, sigma t to the fourth. You balance these two things together. We need to know something about the properties of the grain. So the absorption efficiency is on the order of unity. However, the grains are not perfect black bodies. That is, they keep a little bit more of the heat internal than they actually radiate. All right, so it's a little bit slower to release the energy. So the emission efficiency is lower than the absorption efficiency. If I take a 0.1 micron grain, I stick all these things, I can solve for the temperature, and I find that the temperature of the material at 1 AU was on the order of about 500 K from this very simple calculation. So that tells you, or suggests, that the Earth formed without the stuff that we're made of. That's kind of interesting, right? And so here's a more detailed calculation. What I did is I just took a bare grain and I stuck it with nothing between that grain and the sun in that little simple calculation. But of course that's not the reality. There's lots of other grains, lots of all tiny little grains between that one grain and 1 AU and the sun. So you have to do proper radiation transfer. You have to solve, basically the propagation of radiation through the medium, which happens to be a dusty, what we call protoplanetary disk. One example of this type of calculation is done by Sarah Dotz and Robinson. So this is temperature versus radius. Very hard to see, but I don't want to get you to dig into. This is the line where water evaporates, and then she evolves it. And over all times at 1 AU, which actually it's hard to see here, you never get below the temperature where water will freeze out, and organics, and you're clearly not going to get the CO. Okay, so that's one little problem in terms of incorporating volatiles into the Earth. All right. There's another interesting little problem, of course, is that planets are born very, very high. So you can look at what happens to the Earth as it's born. So you can take the gravitational potential energy. All right. So you have the energy, and you integrate over the Earth's mass function, right, with radius. So here you have the mass of the Earth with radius. You can solve for that energy, and the total accretional potential energy for the Earth is on the order of about 10 to the 32 joules. What am I going to go from this? So here you can figure out the temperature change if you take that energy and the specific heat for what the Earth is made of. All right, if you put all the Earth and you stuck it all together at once, that's not what we think happened, of course, you would heat the planet to 40,000 degrees Kelvin. All right, now, the liquid phase for the Earth, if you were to heat the Earth up to 1800 K, you would have liquid Earth. All right, if you go at about to 3300 Kelvin, you would vaporize the Earth. That obviously didn't. But if you instead, if you think about it this way, if the Earth only received a fraction of this energy at time, it likely suggests that you went through this phase here, and maybe partially this phase. That is, that you went through, clearly probably went through phases where the Earth had what we call magma oceans on the surface of the planet. And perhaps some impacts could actually vaporize some portions of the planet itself. In fact, the moon forming impact is thought to have done that. All right, so we have a magma ocean. What happens at that point? Well, if you had water present on the surface at that time, actually the water could react with iron, and that would go to FeO. And we know that when the Earth was in this phase, the Earth differentiated. Right? That is, the heavy things stuck to the center of the Earth. So the Earth has a nickel-iron core, right? And so you went through this phase of differentiation. You could actually take some water and bring it to the core. All right. Now you may have water present in abundance above and beyond that of iron. Oxygen is significantly more abundant than iron, so the Fe cannot capture all of the water and bring it with it to the core. And you can actually, if carbon is present, you can actually stick a significant amount of carbon to the core. So how then did you get volatiles to the Earth, the stuff that life uses? Well, you probably needed to supply, perhaps, material throughout this process, so that after things were still supplied, after the Earth formed, after the core formed, or perhaps you supply so much of it that the iron and nickel and the various things that go to the center of the Earth can't take it all. So you then, to get volatiles to the Earth, you either have to get it from the gas in the nebula, or you again have to deliver it. And so what is the timing for these various processes? When did the Earth's core form versus when did you perhaps supply material? Okay, well, there's actually some really, really cool ways to figure out how the Earth was born and when the Earth went through this differentiation phase where the core formed. And that is that the core formation, of course, fractionated the Earth, right? That is, the density of the mantle is different than the density of the core. There are lighter elements in the mantle than there are in the core of a planet. All right, and so the geochemists classify the elements in the mantle as lithophile, that's so-called rock-loving elements, versus siderophile, metal-loving elements. Those are ones that go to the core. And what the geochemists do is they use an extinct nuclide pairing of a lithophile parent and a siderophile daughter that is active during the process. And you can use this actually to determine the age of the Earth's core, the core formation basically. So what they do is hafnium, which is a lithophile, decays to tungsten, which is a siderophile, and the half-life of this is a very short 9 million years. So how does this work? Okay, so you have an iron core forming in a meteorite. It's a body that has basically meteoritic ratios for hafnium to tungsten. So you take meteorites as what we think the chemistry of the Earth was like. All right, now meteorites are representatives of the asteroid belt. We actually have no rocks that are representative of the Earth prior to its formation. So that's one little problem. But we do the best we can. So meteorites are representative of, maybe 2-ish AU away from the sun, but they provide us with the initial hafnium to tungsten. Now, when the core forms, all right, you steal all of the tungsten and you stick it in the core. All right, so any tungsten that you then have after the core has solidified, all right, any of this W here, is going to come from this decay. All right, so that's kind of neat, right? The stuff that's left in the mantle is then going to tell you what happened when the core formed. So if the core formation has to then occur during a time frame so that this product is 9 million years, right, is this decay period, all right? So core formation has to occur during the phase where this thing is decaying. So during the first, say, 100 million years of the Earth being alive, all right? So there's a really nice paper by Wood in 2011 that talks about this, and then Doffus and Schausside in 2011. And the estimates actually, so this is what it goes, the core formation here is, right? And then up like this, and this is where the Earth lies. And according to this, they get on the order of about 30 to 40 million years, but could be as much as 100 million years. So that's kind of cool, right? We can actually date and understand something about when the Earth went through these phases and when actually, if you will, the Earth became the Earth. So tens of millions of years. Now, I told you that we had an idea from the moon as to the bombardment of the Earth and the impact rate and so on and so forth. So this is one plot of that, okay, by Kevin Zonley. So this is the impact rate versus time, and maybe it went down, up, down, up, down, down, and some people model it as sort of a decaying rate or a decaying rate like this, and there's suggestions that there might have been what's called the late heavy bombardment, where somewhere around the 3.9 billion years you had a spike. This again is from the moon. The Earth has an effective cross-section that's 20 times that of the moon. So the moon was getting its butt kicked. We were getting everything, right? 20 times what the moon got. So here we go. This is an idea of the impact rate, right? The Earth's core forms way back here, right? Tens of millions of years. Life somehow happened right here, so this thing is decaying. All right. Now, so you can get the needed materials that life uses from these impacts. That is, the material that's supplied to the Earth could have originated from greater distances from the star where the volatiles were incorporated. Those things exist. Well, meteorites have organics in them. Meteorites have water in them. They do. There's comets, of course, which are gigantic dirty ice balls in space. They're mostly dirt with some ice in it, hence they taste like sand. And so you could, by the impacts from material that formed further away, you could have perhaps gotten the stuff that Earth used. Another idea is that perhaps if all the carbon and stuff is in the gas, maybe the Earth got it from the gas. And so the Earth actually is thought over time to have had two atmospheres. There was what's called a primary atmosphere, which was gas captured from the nebula, which would have been rich in volatiles, water and other things. But it's generally believed that the first atmosphere was lost, okay, based on the noble gases, which are closer to meet Earth than the Earth. And so instead, the Earth's atmosphere is generally thought to be secondary, that is, generated by subsequent outgassing. So what that suggests is it's a little bit harder to get the volatiles by this way than it is to get the volatiles by this way. But again, that's something that I'm going to talk about in subsequent lectures. So, astrobiology. So volatiles are delivered to the Earth by impacts. They would have been implanted in the atmosphere upon the impact. And one part of in astrobiology is trying to understand how the volatiles became implanted into the impactors. And so in subsequent lectures, I'm going to talk about comets, asteroids, the Earth, and eventually I'm going to try and tie it all together and ask how you can make an Earth that looks like the Earth. And I think I'm just going to stop right there and take whatever questions. I have no idea how much time this took, so